Just waiting for the recording to start. All right, recording has started. All right, good afternoon, everyone. This is the Unit 4 test review. This is actually a re-record because the morning session, the first half went good, second half just fell apart in so many ways. And I really felt it merited a redo on my part to re-record so people watching it won't be scratching their head like, what is he doing? What's going on? Why is everything falling apart? Because that's what I was wondering. Okay. Okay, first question. We want to use identities. We want to simplify this fraction, cosine of negative theta times cotangent of theta all over cosecant of negative theta. So what we want to do is whenever you see something you're simplifying, if you have cosine, sine, tangent, cotangent, secant, cosecant, and you have a negative theta in this case, we need to change all these so it's a positive. So you would use your odd even identities. Cosine of negative theta just becomes cosine theta. Cosecant of negative theta, well, that's right here. That becomes negative cosecant of theta. And then in the same step, we can also change, I don't think I change it yet. Let's just go ahead and change these first. I don't think I did more than that in one step. Oh, I did. Also in the same step, and we could have saved this, cotangent, we would use not the reciprocal, we use the quotient identity. Cotangent becomes cosine over sine. So our goal when you simplify this is, well, along with using these identities here, the odd even, we want to write everything in terms of sine and cosine. So we did that. Cosecant would be the next step. We would have to rewrite this as well using the reciprocal. Cosecant is 1 over, there it is. So like, where is it? Cosecant is 1 over sine. So that's what gets replaced right here in the next step. All right, then from here, you have the numerator divided by your denominator. So we're going to flip and multiply your denominator here in the next step. So we get the top stuff times the bottom stuff, but flipped, and negative 1 over sine theta. When you flip it, it becomes negative sine theta divided by 1. Well, anything divided by 1 is itself, so that's why I didn't include it in this step. There's no need, but you are more than welcome to put all over 1. It's not going to change anything. And then from here, we can now simplify a little further. All right, so it looks like sine theta and sine theta can cancel out because one's in the numerator, one's in the denominator, and this is all multiplication. And what you are left with would be the negative cosine times cosine. And multiplying those together, you get negative cosine squared of theta. And then that is our final answer. Yep. Right, word problem, law of sines and cosines. Right, so this was a word problem. It says from where you are standing, you see a fountain 60 feet away. You turn 78 degrees and see a pond 110 feet away. How far apart is the fountain from the pond? Round to the nearest tenth. So when you have word problems, I like to draw pictures or diagrams, and I think all of you should as well. So based on this word problem, we want to draw a diagram. And because, well, we're dealing with triangles, it's going to be, well, a triangle diagram. It doesn't matter what angle you start at. I make us, you, right here, but it doesn't matter. So angle A is going to be where we are standing. It says that we see a fountain 60 feet away. So here's the fountain. I call that angle B. And the word problem says it is how many? 60 feet away. We then turn 78 degrees. And then I see a pond. Well, that pond I call angle C. And that pond we know is 110 feet away. We want to find the distance between the pond and the fountain. So if this is angle A, that means this is side A. If this is angle B, opposite of that is side B. If this is angle C, opposite of this is side C. We all know that from before spring break. So we label that this. Now you have to decide if you're going to use the law of sines or the law of cosines. So we learned little tricks of how you can decide, and you can check back your notes for those tricks. Or you can just totally just flip a coin and just try one of them. And the thing is, if you try the wrong one, you're going to run into a big problem. You're going to get stuck in a really bad way. But this one actually is the law of cosines. We have angle A is 78 degrees. That is the inclusive angle to side C and side B, which are given. So, well, that's law of cosines. So we're going to use that. And we just plug stuff in. And then from here, we're going to square root both sides because we're solving for side little a, lowercase a. And we're going to type that in. Now, we got to make sure that because this is in degrees, your calculator also needs to be in degrees. So before you type all this in, make sure you are in degree mode. Because if you're in radian mode, your answer will be very different and very wrong. And that's bad. Little case a, that's right. All right, so we type all this stuff in, and then you should all get this big number, well, this long number, but we want to round to the nearest tenth, which is 1 decimal place. So that becomes 113.8 feet. So for this problem, draw a picture. All right. All right, angular velocities. So another word problem. This one says a tire spins at 27 pi over 4 radians per minute. How many seconds are required to complete 5 revolutions, round to the nearest tenth? All right, this is a stoichiometry problem like you learned in probably chemistry is where you're taught stoichiometry. Is that right? Yeah, okay. Yeah, so I think you learn it in chemistry, but you can apply it to, well, different math classes where needed. All right, so we know radians per minute. This is angular velocity because it talks about radians per time. If this was, let's say, feet per minute or miles per hour, that would be a linear velocity. So angular velocity, I know it's kind of a giveaway in the title of my slide here, but that happens to be a coincidence. Radians per minute, we know right away because it's radians per time. That is angular velocity. It's important to know the difference. An angular velocity versus a linear velocity. They're similar but very different. All right. So there's actually a few ways to solve this problem. So I think this way on this page is probably going to be maybe the easiest. All right, so we know that it's 27 pi over 4 radians per minute. You can even think of this as 27 pi radians in 4 minutes. It has the same meaning. All right, so we want to convert this to, well, let's see, we want to convert this to seconds because this wants to know how many seconds. So, that's key. Right now we are in radians per minute. So let's see. But before we do that, let's convert radians per minute to revolutions per minute. And we all know that in a unit circle, one rotation, so one revolution is 2 pi. So that means we're going to have 2 pi radians on the bottom and then 1 revolution in the top. That's the conversion. One revolution every 2 pi radians. We know that. That makes sense. All right. So kind of jump into the cancellation part, which we can do. We want to cancel out radians and radians. So now we have revolutions per minute. We want revolutions per second because, well, the final answer wants it in seconds. So let's convert minutes into seconds. And we know that we have 60 seconds in 1 minute. So we're going to put the minute on top and the seconds in the bottom. Because if we didn't, we couldn't cancel them out. Minute in the bottom, minute in the top. So those cancel out. So now we're left with revolutions per second. We're on a good start. All right, so we're going to multiply across top and bottom, and we're going to reduce. So that's how we get 9 over 160 revolutions per second. All right, so we're getting closer. Remember, our goal is to know how much time, how many seconds is required to complete 5 revolutions. So right now we know that we have 9 over 160 revolutions per second. We can also look at it as being 9 revolutions per 160 seconds. It has the same meaning, just looking at it differently. So we can set up a proportion using that. So we're going to have 9 revs over 160 seconds, and then it's going to equal. Now, remember, we want to know how many we want to know how much time to make 5 revolutions. So on the other side of the equal sign, we're going to have 5 revolutions, and then on the bottom, we're going to have X seconds. And there's your proportion. Now, this is one way to solve this problem. There is another way to solve this. Actually, I can think of 3 ways to solve this problem. This one might make the most sense, might be the easiest, so I did it first. All right, and then we just solve for x. Well, we can just, cross multiply. But we get that 5/9 times 160. I skipped a few steps by using the diagonal trick. And then we just type that in, hit enter, and then you will get 88.8 repeating. Nearest tenth would be 88.9. So 88.9 seconds. That is the final answer. All right. On this next page here, I do the same problem. I'm just going to show the work. I did a little differently. I solved this problem by converting my radians per minute to radians per second. And then I used this 2 pi radians equal revolution. We know that. Multiply both sides by 5. So 5 revolutions is equal to 10 pi radians. That makes sense. Then from here, using this, we set up a proportion that way. 9 pi radians over 80 seconds equals, we want to know how many radians. Well, 5 revolutions is 10 pi radians. That's on top. X seconds, and then we just solve it just the same. I think this way, it makes sense, but maybe not as much sense. So maybe the previous page is probably, I think, easier to understand. But this is another way, and I can still think of one more way to do this problem, but I don't show it. All right, next problem, area of a triangle. So in triangle EFD, measure of angle E is 132 degrees. Side EF is 11 inches. Side ED is 5.6 inches. And then we want to know what the area of the triangle is. We want to round to the nearest tenth. All right, so probably want to draw a picture. So I think I do draw a picture right here. It doesn't matter what your triangle looks like. I try to draw mine to scale just because I knew what the answer was. So if you know the answer, you can draw a triangle pretty close to what it looks like. But as long as you have a triangle and you have size DEF, I'm sorry, not DEF, EFD, even though it doesn't really matter. Once you get EFD, it just starts over. So triangle DEF is actually also correct. Um, anyway, I labeled my angles DEF, and then it says measure of angle E is 132. So that's what I labeled that as. Um, side EF is 11 inches. So there's my 11. And side ED is 5.6. And then this other side, we don't know. And well, we really don't care. So we have two sides and the inclusive angle. So we have three choices, plus the one you learned back in grade school to find area of a triangle. And the one that we're going to use is that first one, K equals 1/2 times your two adjacent sides times the sine of the inclusive angle. So we plug all that stuff in. And again, make sure you are in degree mode because, well, we're talking about degrees here, not radians. So typing all this in and hitting enter, and we're going to round to the nearest tenth. We should all get the correct answer this time. This morning, it was a big mess, but it should be 22.9 inches squared. People that were here this morning, is that correct? Okay, good. I'm on a roll then. And people that are here, feel free to interrupt me if you have any questions. All right. Central angles. We want to find the radian measure of the central angle whose radius is 10 inches and arc length is 35 pi over 3 inches. All right. Well, we're going to go to 4.07 and we're given a nice formula in a diagram. So arc length is S equals radius times the angle, the central angle it is. And you are given some pieces. So get my pen. The radius is 10 inches. So I'm going to label this 10. So there's 10 inches. And then the arc length. So this value right here is your arc length. And then we want to solve for central angle theta. So we just plug in the stuff that we know into this formula here, and there's your setup. We want to solve for theta, so we divide both sides by 10. And then really from this step, you can type in 30. So if you do type this in from this point, all of you should know that you need to put your numerator in parentheses. It does matter. It really does. And really, you can just type that in and hit enter. But to kind of show a little extra steps, you have a fraction divided by 10. We're going to flip and multiply. So somebody asked me earlier this morning, how did I do that? Well, remember that 10 is the same thing as saying 10 over 1. So when you flip and multiply, well, that 10 over 1, the 1 goes on top, 10 goes on bottom. So that's where that 1 came from, if you're wondering. And then we just do the maths. And the angle becomes 7 pi over 6. And really, if you typed this step in correctly, you would have got the same answer. I like showing a little extra work. I like doing, work by hand. And I'll use my calculator if I absolutely can't do it by hand or on paper. I think it makes you smarter that way. Maybe, I don't know. If only people watching the recording could read chat, it's funny. Mm, that's funny. All right. Chat is where the magic happens. That's funny. All right. Next problem. Okay, some difference identities. Okay, you're given the cosine of angle is -3/7. Then this says that your angle is greater than or equal to pi/2, but less than or equal to pi. So this is telling you which quadrant you are in. Now, because we're greater than or equal to pi/2, that's 90 degrees, and pi is 180 degrees. This puts us in quadrant number 2. So I'm kind of jump down the bottom here. I'm going to draw that picture. So I'm going to draw a triangle in quadrant 2 with everything labeled appropriately. So the cosine of the angle, remember, so SOHCAHTOA, cosine is adjacent over hypotenuse. So looking at the angle, these are called reference angles. We're going to have adjacent is your 3. So there's your 3. And then hypotenuse is 7. Well, there's your hypotenuse 7. And then you're going to use, once these are labeled, because we're in quadrant number 2, we know that the adjacent is negative because that's the negative x direction. This would be the radius of your circle if I actually drew a circle to represent this. You use the Pythagorean theorem, a squared plus b squared equals c squared. So I don't have the work on here, but I trust everyone in pre-calc is more than capable of doing the Pythagorean theorem to solve that side that I have in blue because I don't show the work. All right, next one says the tangent of beta is 2/3. It says that, ooh, I have a typo. Okay. This should be beta because obviously we're talking about this angle and nobody caught it in the morning session. I just caught it now. So this is really should be beta is greater than or equal to pi and less than or equal to 3 pi/2. So this is telling us it's greater than 180 degrees, but less than 200 and 70 degrees. Is that what that is? 270? Math is hard right now. Yeah, okay, 270. So this tells us we are in quadrant number 3. So we're going to draw a triangle in quadrant 3. And we're going to have this stuff labeled. So remember, tangent is opposite over adjacent. Remember, SOHCAHTOA, tangent, opposite over adjacent, 2/3. So opposite of this angle is going to be your 2. And then adjacent, well, there's your 3. And because we are in quadrant number 3, x is negative and y is negative. And then again, we have to find the hypotenuse using the Pythagorean theorem, a squared plus b squared equals c squared. I trust all of you can do that, and you should get radical 13. All right, so before I show the next step, I'll show the next step, and then we'll come back to my thought. All right, so the sum and difference of identities, it wants us to find the cosine of theta plus beta. So we go to our formula sheet, we look to where that is, and I copied it down for us to see. Your test may be different. It may be, it may want sine or it may want tangent or something. So here's cosine. Now, something to remember when we learned this a couple weeks ago is when you have the cosine of alpha, and then if you notice, this is plus minus beta. And then over here, it's actually opposite. It's minus then plus. So this matters. Now, because we're doing the sum, we want the top operator. Because we're doing the sum, we want the top operator. So over in the expanded side of the equal sign, you also want to use the top operator. And the top operator over here is a minus. So be careful. So that means we are going to use this form. The cosine of theta plus beta is equal to cosine of theta times cosine of beta minus sine of theta times sine of beta. So everything is in terms of sine and cosine, right? So we have a cosine, cosine, sine, and sine. So we need to write both theta and beta in terms of sine and cosine. Well, this top one is already in terms of cosine. I just need to rewrite this using our triangle for the sine. So I'm going to do that right next to it. Now, if I was smart, I would have typed this out when I made all my corrections earlier, but I didn't. All right, so sine of theta is equal to, remember, sine is, so SOHCAHTOA, opposite over hypotenuse. So opposite from theta down at the triangle there is 2 radical 10. And then hypotenuse is 7. So now we know what the sine is. So that's good. All right. For tangent of beta, let's write sine and cosine. All right. My mic's in the way. All right. So we want sine of theta, and we want cosine. You know what? It's beta, not theta. Let me write that just for correctness, even though I think all of you know what I'm doing. So we want sine of beta. All right. So looking at beta, sine is opposite over hypotenuse. So we're going to have -2 over radical 13. And then for the cosine of beta, well, that's SOHCAHTOA, so adjacent over hypotenuse. So adjacent to angle beta is -3. And then hypotenuse would be radical 13. So if you're watching this and you're thinking, hey, we need to rationalize your denominator, you are kind of correct. You have a choice. You can actually rationalize now, or you can rationalize in the final answer. Because all we're going to do is use what we just wrote down to actually plug into this formula. It's probably wise to rationalize at the very end. I think it'll save you a bunch of steps. And I think the math is actually easier if you wait. But it really doesn't matter. It's really up to you. So I chose to rationalize at the very end. So I'm just going to replace all of that stuff with what we found. Cosine of theta, that's given. That's -3 over 7. So that's what I wrote here. Cosine of beta, well, that is -3 over rad 13. That's down here. We found that. Minus, don't forget your minus sign. Sine of theta, well, sine of theta is 2 rad 10 over 7. So there's your 2 rad 10 over 7. And then times your sine of beta. And sine of beta, well, it's right down here. It's -2 over rad 13. So we just, we drop those in and then we do the math. So we have to multiply these two together and then multiply these two together. Remember, there's a minus sign between these. It's going to be this stuff minus this stuff, whatever we get. So let's do that math. And we get that. So you get 9 over 7 rad 13. And then we have plus, well, that's because this is a negative. So we have negative this fraction times negative this fraction. So a negative times a negative gives us a positive. And then, this times this is 4 rad 10. 7 times this is 7 rad 13. All right. So now that we have these two fractions, To add two fractions, we have to have like denominators, which we do. 7 rad 13, 7 rad 13, which means I can now add our numerators together. We're going to have 9 plus 4 rad 10 all over 7 rad 13. So that's what I show in this next step. And now from this step here, so we don't want to leave your final answer as 9 plus 4 rad 10 all over 7 rad 13 because, well, we have to rationalize. So don't stop here. We rationalize. I show the work. Multiply top and bottom by rad 13. That's how we get 91 on the bottom. Now, because you have two terms on top, don't forget, you are multiplying rad 13 by the 9 and by the 4 rad 10. And that's how I get this. So if it helps to write it like that, and you're just distributing, right? And then you're left with that final answer. And that is reduced. So remember, when you have a fraction like that, if you want to reduce this fraction, you want to look at the 9, the 4, and the 91. And you want to reduce all three numbers by the same factor. Well, I believe 91 is prime, so that kind of stops us from doing anything else. But if 91 wasn't prime, let's say 91 was just 90, and you had 90 on the bottom, and you had 9 on top here, and you have 4 on top, well, 90 and 4 would reduce, but 90 and 9 do not reduce. So it's all or nothing. So keep that in mind. And then the final answer, I think I rewrote this. I did. So I put the rad 130 first, only because it's bigger than 13. And I think that's how your test wants it too. I believe in your test it's like a drag and drop. So they just swap those two. It means the same thing. So get your 4 rad 130 plus 9 rad 13 all over 91, and we're done. All right, everyone in chat, we're doing good. Is this easier the second time around? Yeah, me too. Yeah. Me too. Me too. All right. Solving. So we want to solve the solutions to the trig equation of the intervals 0 to 2 pi. So one rotation. So all the answers must be between 0 and 2 pi. All right. 2 sine squared of x equals rad 2 sine x. So if you are watching this and you are thinking, hey, I can divide both sides by sine x. You are mathematically you are correct. You can divide both sides by sine x. You really want to avoid doing that because even though mathematically it's correct, you actually lose some of your answers. So when you solve trig equations, you want to avoid dividing by the trig function. Not always, but I would say, I don't know, it's hard to say percentage. I would say most of the time. How about most of the time for this class? Because when you divide stuff out and you cancels out, you actually lose it. And that matters. So we want to factor. So you want to subtract rad 2 sine x both sides. And then you want to solve by factoring. So now we're just going to factor out sine x in front. So greatest common factor. Once it's in factored form like this, we then set the factors equal to 0. And we solve them separately. So let me do the right one first. So if you think about it, in the very beginning, if you divided both sides by sine x, you would have got down to this step immediately, right? 2 sine x equals rad 2. People in chat, you see that? But the problem with doing that, if you divide both sides by sine x, you get down to here. That sounds like we saved a lot of steps, and that's cool and all. But now we're only solving one equation and not this equation too. See how you're losing out on these answers. And that's why you don't want to, well, divide by trig functions to cancel them. Yeah, uncool. Yeah, it's not cool to divide by trig functions when solving. Bad things happen. You'll lose half your answers. All right. Let's solve the left one. Okay, so sine x. You want to use your unit circle because if you type in from here, you want to solve for x. You inverse or arc sine both sides. You type that and you hit enter. You only get one answer. Well, remember the unit circle. It says that we want from 0 to 2 pi. So you have to use a unit circle. All right, so arc sine both sides. Remember, sine is y, so you want to know on your unit circle, which all of you should have. I have mine printed out and have some stuff written on there too. But you want to look to see when your y value is equal to 0. Well, your y value is equal to 0 in 2 places. X equals 0 and, I'm sorry, not x equals 0. At angle, radian, 0 radians, and also at pi radians. So there's those 2 answers. And if you type in arc sine of 0, hit enter, you will get one of those answers, which you would get 0, right? But it wouldn't give you pi. So don't use your calculator. All right, next one. You want to divide both sides by 2. And then you want to arc sine both sides. So then the question is, well, if you arc sine both sides, we want to know the radian, the degrees, or the radians. We're talking about radians here for the answer. When y equals rad 2 over 2. From the interval 0 to 2 pi, well, it's positive rad 2 over 2 in 2 places. The first place is in quadrant 1. Second place is in quadrant 2. And those radians are pi over 4 and 3 pi over 4. And then we just stick all the answers together. And then there's all 4 answers. All right. Doing good so far?
We discovered earlier GeoGebra also.
Oh, yeah. So Emily says that if we go to GeoGebra and we type this in, GeoGebra gives you all 4 answers. Isn't that nifty? So if you're watching this review, maybe you want to go to GeoGebra and try that out to see if you get all 4 answers. I think that's pretty neat.
Just Sarah, just put in the original equation that 2 sine squared of x equals rad 2 sine of x.
Okay, and it does it for you. Nice.
The one quiz about this was like the only thing that made me not fail it.
Good. All right. So it's a good way to do it by hand and also check it in GeoGebra. Remember, you can't use GeoGebra on your SATs. Keep that in mind. But I don't think this is on your SATs to begin with, so I don't know. Do what you want. All right, area of a triangle. All right, we want to find the area, answer in simplified radical form, so no decimals. All right, so we give you all 3 sides of your triangle. So looks like we can use Heron's, I'm going to call it Heron's formula or Hero's formula, it's also called. That is that. Remember, your S is all 3 sides added up divided by 2. All right, so we just plug that stuff in. We got to solve for S, and then once you have S, we know A, B, and C. It doesn't matter the order, which is A, B, or C. You just got to plug them in. So S is 21. We plug everything in. And then you can just type this all in at once, or you can just simplify what's inside. I think I typed everything in. I don't remember. Oh, I did. Yep, I did simplify it. So hopefully my numbers are all correct. 21 minus 11 is 10. 21 minus 15 is 6. 21 minus 16 is 5. That looks good. And then type this step in. And remember, we want simplified radical form. So we got radical 6300. Simplified is 30 rad 7. Hopefully you have a calculator that does that for you, like the FX115 or FX300. Those are about $15 and $12 respectively. I think those are probably, in my opinion, probably the best calculators for that cost. I think the Casios are a better value than Texas Instrument, but I do like the TI graphing calculators better than the Casios. But anyway, they're always trying to make that dollar, right? Okay, so we have 2 gears connected by a chain. The angular velocity of the smaller gear is 25 pi over 5. I'm sorry, 23 pi over 5, not 25. 23 pi over 5 radians per minute. The larger gear has a linear velocity of 161 pi over 75,000 meters per second. What is the radius of the smaller gear? In centimeters. Okay, so we got a few problems going on. And I said in the morning class that this is not a physics class. This is pre-calc and trig, which goes into physics, but this is not a physics class. This test question doesn't take into account, I think that somebody in class said that you had a question in your module somewhere that was like this. I couldn't find it. I gotta message that student and ask where they found that because I didn't see it. But did you know that when 2 gears are connected by a single chain, like let's say your bicycle, the bicycle, the crank, and then like the rear, it's called a cassette, the gears. Well, that's 2 gears connected by 1 chain. Did you know that the linear velocity of both gears are the same? Science. Now, if you think about it, this kind of makes sense. If you really think about this chain being connected by, like, let's say, like 1 big gear, then 1 smaller gear. Remember, linear velocity doesn't take into account angles. So that chain, no matter, like, think about the chain, and then you pick a link, and then you follow that link, and you're pedaling the same speed. No matter if you're going around the big gear or the little gear, that link is moving at the same linear speed. So remember, linear velocity would be like, in this case, it talks about meters per second. So meters per second, that link is going the same meters per second, no matter where it is going around those gears. But the angular velocity of the connected gears are different. That kind of makes sense. So you think about a big gear, the angle. So you're on the outer part of the angle or the gear, and it goes around, right? It may appear to be going slower because you have more teeth that has to the chain has to, I guess, make contact with and make a full rotation. But a very small gear that only has, like, I don't know, let's say 5 teeth. It only takes 5 teeth to do a full rotation, right? So the angular velocity of the little one is much faster than the angular velocity of the larger one. So I don't know, something to think about or not think about. I don't know.
Just really quick, I'm pretty sure the question like this was actually on the quiz for that lesson. If I'm correct, I'm not sure if I am or not, but I seem to remember something like this on the quiz, not in the module.
Yeah, it was on the quiz.
Oh, well, that's tricky because this information would have been nice to know, right?
Yeah, I don't remember this anywhere in the module, and I go through the modules very carefully.
Okay, I'll ask Chloe. Maybe she meant it was on a quiz, but she's the one that said that she saw it. I'll ask her again. All right, so here's this information. That's nice to know. Actually, you need to know it for this problem. Now, because linear velocities are the same no matter if you are on by two gears connected together, so that means the linear velocity. Oops, let me get my pen. The linear velocity for the larger gear. This means the linear velocity of 161 pi over 75,000 meters per second is also for the smaller gear. Well, because by the fact that I tell you this, science. So that's, you need to know that. All right, so let's go to the next page where I have all this work. I like physics. I always wanted to teach it, but then I didn't want to teach it because it's a lot of work to teach physics. It's a lot of prep work to teach physics. So your physics teachers, if you take physics in high school or college, good for them. They have more willpower than I do. It's a lot of planning. But anyway. All right. So angular velocity of the smaller gear. Well, so we're just writing down the given stuff. All right. So angular velocity is that was that omega, lowercase omega, is equal to, well, 23 pi over 5 radians per minute. We know that. The linear velocity of the larger gear. So again, when I made this, my corrections, I should have also wrote that this is larger and smaller. Remember, because linear velocities are the same when they're connected by the same chain. So linear velocities of the larger and the smaller is the given, which is 161 pi over 75,000 meters per second. All right, so we wrote down the given stuff. We really actually haven't done anything in this problem. This problem wants us to find the radius of the smaller gear in centimeters. Well, right now we are talking about meters per seconds. This up here is radians per minute. So we probably want to make, well, we need to make them both in terms of the same time, whether it's radians per minute and meters per minute, or radians per second and meters per second. We have to have the same time units. So, and it's your choice. It really doesn't matter. If you want to make radians per minute to be radians per second, use stoichiometry and mess with the omega equals that stuff. Or if you just want to mess with the meters per second and make it per minute, mess with that one. And that's what I did. Also, I chose to mess with this one because we need to make seconds match this to minutes, and we need meters to be centimeters. So I said, why not? Let's just mess with one of them and not both of them, right? All right, so let's convert meters per second to centimeters per minute. Let's do that first. So it looks like talking about meters and centimeters, we know that, well, the metric unit is superior to I think we call ours the standard something. I should know this. But Americans and I think maybe some other countries, we like to use inches and feet and miles, and it doesn't make sense. It really doesn't, because all physics uses the metric system. If you go work at NASA, you are going to use meters and kilometers. You are not going to use feet and miles. It's ludicrous. There's actually a kind of off topic. There's a story, you can probably Google it, where there was like a multi-million mistake where there was a programmer, maybe multiple ones. One programmer used like feet per second, but the other program, who probably did better in physics than him, used metric meters, per second. Well, when their code came together and their satellite needed to like orbit, instead of orbiting the planet, it decided to crash into the planet, and $1 million just blew up. So yeah, it's a true story. So yeah, it's too bad we can't all switch to the metrics system. But if you saw the speed limit on the side of the road and it says, please only go, what is it, like 60 kilometers per hour, no one would understand what that means. They don't have like a sense of understanding of how fast that really is. But if I said, go 25 miles per hour, you can, without looking at a speedometer, you can kind of guess and get really close to what 25 miles per hour is. So we will never change because we're stuck in the bad ways. Good job, America. All right. Anyway, so let's convert this. So we know that there's 100 centimeters in 1 meter. So remember stoichiometry. So now we can cancel out meters and meters. So meters cancels out and meters cancels out. That's good. So now we're at centimeters per second. So last thing to do is convert seconds into minutes. We know that there's 60 seconds in 1 minute. So we're going to use that conversion to get to here. And that means we can cancel out seconds and seconds. So now we're left with centimeters per minute. We're doing pretty good. All right, multiply the top stuff together, multiply the bottom stuff together. You get that, reduce it. Your calculator would do it for you. It's kind of nice. So you get 322 pi over 25 centimeters per minute. So look, we're getting a little closer. We have radians per minute for the angular velocity, and we have centimeters per minute for the linear velocity. We are in terms of centimeters, which is what the final answer will be, in just centimeters. And both of these velocities, angular and linear, are in terms of minutes. They match, and that's a good thing. If they didn't match, we couldn't really do anything. All right. We're going to use the formula. V for linear velocity equals radius times angular velocity. So this is from our 4.08 lesson. We know linear velocity. We know angular velocity. We're trying to find the radius. So we just plug this stuff into this really simple equation. Looks like this if I typed it right. Thank goodness I did. Oh boy, that's always nice. Solving for r, so multiply both sides by 5 over 23 pi. Or divide both sides. Multiplying by the reciprocal actually would have been a smarter way to show it, but I don't do everything the smart way apparently all the time, only sometimes. I don't want to appear too smart. Then I wouldn't be human. All right, so we just type that in. You can flip and multiply. which we actually should have just done that from the very beginning of multiplying both sides by the reciprocal. That actually would have been smarter if I would have thought to do that, but I didn't. So here we are. So we type that in, that fraction times that fraction, you hit enter, and we get 14 over 5, and we are going to round. I don't tell you to round to anything, do I? Well, I probably meant to tell you to round. 5, 7, 14, 9 over 5. Oh, never mind. It just works out that way. Yeah, 2.8. Rounding is not needed because it equals 2.8. We are not playing Among Us, people. All right, so 2.8 centimeters. So this problem, this is a lot of prep work. But once you actually have it set up, it's plug and chug. It's using the stoichiometry to get everything to work together. They both, angular and linear, have to have the same units in terms of time, so per minute and per minute. The linear velocity needs to, well, have the units that the answer wants to be in, which I tell you I want it in centimeters, and we're in meters, so we have to convert that. We actually could have probably converted the final answer. If you left it as meters per minute, your final answer would have been in meters, and you just have to convert that final answer into centimeters. So you would have had 0.028 meters converted in centimeters, but that way just sounds terrible. Don't do it that way. All right. So I also did that same problem a different way. I'm just going to show it. And you can pause this video and see what I did. I basically mess with both velocities to convert them into per second instead of per minute. And you can do it this way. You just got to mess with both of the given values. But in the end, the setup is a little different, but in the end, the answer will be exactly the same. Math. All right, sector area. All right, so in this morning's review session, this is where this entire review fell apart, like was shattered. From this point on, it was just a disaster. All right, so I rewrote this problem because it was written kind of, I don't know, it wasn't written very well. It was missing some stuff that just didn't make sense. So I just rewrote it. Hopefully it makes more sense now. The one-year test makes a lot more sense than what I did this morning.
This problem is that satellite went new.
Yeah, this broke my brain this morning because everything was just like a big mess. But anyway, all right, this one says a circle is divided into 16 equally sized sectors. 5 of the sectors are colored blue, and the rest are different colors. The area of 2 of the blue sectors is 32 pi over 25 inches squared. What is the radius of the circle? All right, that made sense this time. All right, so these first 3 lines, this is just writing the given information, because whenever you have a word problem, if you can write down in like bullet points of the important info, it just makes the problem way easier to look at and understand. So that's what I do here. The area that was given is 32 pi over 25 units or inches squared. Next question, we ask ourselves, well, how many sectors were used to find this given area? Well, it says that two of the blue sectors were used to find this area. So that's important. So I write down 2. Remember, this is out of, so I in parentheses, I just put out of 16, right? Because that's kind of important to know too. So it's 2 out of the 16. All right. Next line says, find the central angle based on the sector. So if you can visualize or even draw a circle out like a pizza, and if you can just divide it all up and create 16 equally sized sectors, that's what we're dealing with here. So we want the angle of those 2 sectors. Now, the reason why I want just those 2 is because the area is based off of just 2 sectors. So I want the central angle of those 2 sectors. Does that make sense so far? All right. Makes sense this time around. Me too. All right. So remember, a full circle is 2 pi. So remember, a full rotation is 2 pi radians. But we only want 2 out of the 16. So I multiply 2 pi by, well, 2 over 16. And then we just do the math, and we get pi over 4. So the radian measure of 2 sectors is pi over 4. And then we need to use the formula. Area equals 1/2 radius squared times theta. This is the sector area formula. We know the area of 2 sectors. We know the angle. Remember, this is the central angle measure of those 2 sectors. So we plug those 2 values into A and to theta. So I do that right here. So again, this is the area of 2 sectors. This is the angle of those 2 sectors. And then, we just do the math. 1/2 times pi over 4 is pi over 8. And then from here, I would multiply both sides by 8 over pi, the reciprocal. And then I would do the square root of both sides. When we do 32 pi times 8, well, that's 256 pi, and then 25 times pi is 25 pi. Well, the pi and the pi cancel out. That's why they're gone. And we want the answer in terms of, did I say what I want? I don't tell you. So let's just round. But no rounding needed, because radical 256 over 25, hitting enter gives us exactly 3.2. And it's a radius, so it's inches. The end. So this morning, this problem was so messed up. The word problem itself was written wrong. And then the work I had here was wrong in multiple places. It was a disaster. And that's where it all fell apart. But it's all correct now, and it all makes sense. So there you go. This problem is a lot easier than you probably thought. Yeah, we won't talk about my numbers that I had this morning. It was crazy. I don't know what happened. Okay, people in chat, we good to go on? All right. Okay, it says, what is the general solution of the trig equation? Rad 3 cotangent theta equals 3. All right, so we divide both sides by rad 3. Oh, and before we do that, we want to convert cotangent into, well, 1 over tangent of theta using the inverse. Is it called the inverse properties, inverse trig? I have it written down on one of these other pages. Let me see. Of course, it's at the very beginning. Oh, there it is. Yeah, very beginning. Reciprocal identities. That's what it's called. Yep, cotangent is 1 over tangent. So we use that identity, reciprocal. You just click forever. All right. All right, so rad 3 times 1 is rad 3 over tan theta. And then I use a little diagonal trick and I swap tan theta and 3. So then we arc sine tan both sides. So hopefully on your unit circle, you have stuff labeled so you know which angles. You will have 2 choices, right? So looking at, get my reading glasses on here. Looking at your unit circle, you really only have to guess 2 times. So it's either going to be at pi over 6 or at pi over 3. So on my unit circle, I actually wrote down what the tangent value is at those 2 angles, so I don't have to guess. So at pi over 6, tangent is rad 3 over 3, simplified. And then at pi over 3, my tangent of that is rad 3. So I wrote those down, and I told you in the lesson weeks ago that you might want to add those to your unit circle just because we do see it a lot. And trying to guess those or calculate them the same thing every single time is kind of insane. If you write it down once, you can just save yourself those steps. But we need to figure out what the angle is where the tangent of that angle is rad 3 over 3. So pi over 6 is the first answer. So pi over 6 is the first answer. And with tangent, remember, we're using the full unit circle. You can look at the diagonal. So opposite of pi over 6 is 7 pi over 6. So that's where you also get positive rad 3 over 3. So there is your other answer. So in quadrant 1 and quadrant 3, you get this. And then underneath these blue boxes, I just show my work of I'm just validating my answers of, hey, this is how I got that. So at pi over 6, remember, tangent is y over x, so the y value is a half at pi over 6, and the x value is rad 3 over 2 at pi over 6. And I just show the math of simplifying to show, hey, yeah, look, I get rad 3 over 3, which is what we wanted, right? It's just verifying the work. And then same thing for 7 pi over 6. I'm just going to show the work to verify that's true. It's the same thing, but now it's a negative divided by negative, which we all know is positive, and that's why we get the same answer. So there's the 2 answers, but remember, in general form, we have to write those answers, and then for tangent and cotangent, it should be plus pi n, but like this. So here's the answers we would have got, because we're talking about tangent and cotangent. Remember, sine and cosine, secant and cosecant would be plus 2 pi n. Tangent and cotangent, those are plus pi n. We learned that weeks ago. Well, if you look at these 2, pi over 6 plus pi n, and then 7 pi over 6 plus pi n, well, this is redundant. Because when n equals 1, pi over 6 plus pi is equal to 7 pi over 6. So you get overlap. So this one covers this answer. So we actually don't need to write that second one. So the only answer for this one is actually this, that right there. That is the only correct answer for this problem. Writing the second one is redundant, not needed, and if you write it, well, you're not done, and therefore it's wrong. But anyway, however, your test has a mistake that the test creator doesn't agree with me on, even though there's no math book that I could find or source says that it is okay to write your answer that has tangent and cotangent with in general form with what you found plus 2 pi n. The test expert or whatever who wrote the question did not agree with me. Even though I wrote him back saying there's no source that says this is okay. He blocked me, I think. So, but on your test, it's a test error. So in order to get, well, points for it, right? So it grades it correctly. You have to select the wrong answer to make it right. So you have a 1 in 3 chance to get the question involving cotangent. So when you do, and you get pi over 6, for example, or 7 pi over 6, just mind-numbingly put plus 2 pi in and select those, and then you'll be right. So even though these are wrong, they're right. Well, so they are correct. Mathematically, these actually meet the requirements of the previous page, but it's not in general form, in my opinion, based on sources that I found. So anyway, there you go.
This is what you get for coming to the Class Connects or watching them, because if you don't, I don't understand how this wouldn't be extremely frustrating on the test.
It is, yes, I agree. And this question on your test, I think it's like the second to the last problem, maybe the last problem. The good thing is you get a bank of answers, and you just have to drag the right answer from that bank to the little spot. It says, hey, here's my answer. But for that problem, you don't actually get the correct answer as a single choice. So as far as I know, I could be wrong.
Lame.
I know, I agree. So if you happen to do the work correctly, you get the right answer, but you drag the right answer over and it marks it wrong, and you know it's right, message me and I'll grade it by hand. But I know I hate telling you to put the wrong answer to get the right answer, or the graded right. I don't know. You know what I'm trying to say. I can't change it either. I asked. All right. Anyway, there you go. All right, trig identities. So you are given a series of steps, and we need to verify that this equals this. So if you notice, one side of the equal sign does not change. Well, that's okay. That's good. But we want to make this side using identities, which I put here and here. We want to use these identities to go from step to step to step to step to step. And eventually, using identities correctly, we will get the left side to equal the right side. And then that's how we prove. So you did proofs in geometry. I think they're kind of neat. Most people hate them. But this is basically a proof. You are proving that this is equal to this. Now you're given a bank of answers. And I said earlier, people who showed up, do not look at your bank of answers to try to figure out which one gets dropped into these boxes. I promise you, if you do that, you will confuse yourself, and trying to find a pattern isn't going to work. You need to use identities to do the math to figure out what goes in the box. So if you do the math from step 1 to this first blue box, and you do it right, what you get should be one of the answers here to drag. All right, so looking at 1 minus the cosine squared of x all over secant squared x minus 1. Why does everything look blurry? That's why. We want to probably use the Pythagorean identities. Now, 1 minus cosine squared x. Now, you are allowed to manipulate any of these identities to make it match. So this is 1 minus cosine squared. Well, you look here, I can subtract cosine squared both sides of this top line, to make it 1 minus cosine squared of theta equals sine squared theta. So that means this top becomes sine squared theta based on this first identity, the first line. So the top becomes sine squared x. The bottom, secant squared x minus 1. Well, looking over here, secant squared x, well, there it is. But we want secant squared minus 1. So, okay, well, just subtract 1 both sides and make it look like that. So now we'll have tangent squared equals secant squared minus 1. So that means this piece right here becomes, well, tangent squared. Then, once you do that, look at your bank of answers and find the one that says sine squared x over tan squared x, which it exists, and you would drag this one right here. You would drag this to that blank box, and then that first box is correct. Now let's go on. What can we change here? So we got sine squared x and tangent squared x. So I said in the past that you usually want to get your trig identities in terms of sine and cosine. Well, I have sine on top already. Tangent, well, let's change that. Tangent we know is sine over cosine. And because it's squared, well, it just becomes sine squared over cosine squared. That's really the only thing that changes. So sine squared on top stays the same. Tangent squared on the bottom becomes sine squared over cosine squared. And then we would just go to the boxed choices here, and we find where that is. Hey, that's right here. So I have it here, so I would drag it to this, and there's your second box. All right, we're doing pretty good. All right, next, we have sine squared divided by this fraction. Well, whenever you have like the top portion of a fraction divided by a fraction, you want to flip and multiply, right? So we're going to take sine squared multiplied by the reciprocal of that bottom portion. So it's going to be sine squared times cosine over sine, which is this box right here. So we would drag this box, well, to here, because that would be the next step. Then from here, we can cancel out, look, sine squared and sine squared, we can cancel those out. So you are left with cosine squared all by lonesome. And hey, that's one of the choices. That's good. That is good. All right, next, just to kind of just verify the answer, even though we are done with this problem, we should probably verify that cosine squared becomes 1 minus sine squared. And looking at here, this one has cosine squared. So let's go ahead and subtract sine squared both sides, and we would have cosine squared equals 1 minus sine squared. Hey, that's what we have in the next step, so it must be correct. And we are done. Not too bad, I hope. And you should write this stuff out. I know I talked about saying, oh, subtract cosine squared or subtract sine squared both sides, but really on your paper, you should write that out so you can see it. When you involve more senses when you're doing anything in life, not just math, if you can involve your sight along with your cognitive thinking, along even saying it out loud, the more senses involved, the better you are off of getting it correct in the end. So keep that in mind. More senses, the better. You guys should see me talk to myself when I do math by myself. You think I'm crazy, and if we're on a bus, you might not want to sit near me. But it helps. All right. We good so far? keep going. We're almost done, I think. Okay. Oh, that was that was the last one. Now we're on to the TGA stuff. That's good. All right. So first TGA. By the way, every TGA problem, 1, 2, and 3, we did as bell work. A different problem, of course, but and I starred them. So if you have that YouTube link of the class, you can easily go to the YouTube link, and on the channel that I created for this class, excuse me. If you go to playlist, you go to Unit 4 playlist, and you can just kind of click through all the units to figure out which Bellworks I starred really quickly, right? But all of you should be watching the live sessions. I think this class is hard to learn anything without watching those recorded or live sessions, but what do I know? All right, so find the exact value. You need to use the sum difference identities, I think it's called, and your unit circle. Yeah, that's how I want this problem done. You need to use the sum difference identity with your unit circle to do this problem. If you don't do it that way and you just type this in, I will give you 0 credit, because my instructions that I uploaded today state that. You must use that. Typing this in and hitting enter, giving the exact value that way with no work whatsoever gives you 0 points. Just so you know. What's the point of teaching this stuff if you're actually not going to use it at least once? All right, find the solution to 8 sine quantity 3x equals 4 on the interval 0 to 2 pi. So this is kind of a long problem, actually. Kinda. I would say it's long. It's a multi-part problem, and I did do a problem similar to this on a Bellwork. So probably want to check that out if you're confused. It does involve using the general form of your answers to get your list of answers. So there's a hint for you. And the last problem, which is, I think, probably one of the easier problems on your TGA. I would say number 2 is probably the hardest out of the 3. Number 1's the easiest, kinda. Well, they're all kind of, I guess, hard or easy in their own way, but I think 2 is probably the hardest. 3 is probably the easiest. All right, so you and your friends got tricked into helping another friend move stuff from a garage into a moving truck. The ramp used is 12 feet long and makes a 36-degree angle with the horizontal ground. You discover that the incline is just too steep. So you replace the ramp with one that is 32 feet long. What angle does this replacement ramp make with the ground? Round your answer to the nearest 1/10 of a degree. So I did a problem very similar to this. It was different on Bellwork. It was set up. It's different because I think on the Bellwork, I asked for like how long is the ramp, but in this problem, your TGA, I'm asking you the angle of the new ramp with the ground, which is very different mathematically when you do it. Setup could be the same, but math is different. Draw a picture, and for the boarding class, I drew a truck. So there's my truck, and then just to I don't know, kind of get you guys going the right direction, because I did tell the morning class more than I probably should have. So I will tell you guys too, watching the recording, assuming you actually stay around to watch it all. All right, so let's say that first ramp is what? Oops, that's like 2 ramps. All right, so there's your first ramp, and you have some angle with the ground, right? That you're given, and then you're like, yeah, that's way too steep, doesn't work out for me. We need a longer ramp. So you're like, all right, so let's do a longer ramp. This is definitely not to scale, but you get the idea. So there's that ramp. And you're like, all right, well, oh, these should probably, probably connect those. That should be a straight line. And then you have that angle. So hey, look, I created a triangle that has 3 sides and angles and stuff. And then you have to, fill stuff out, figure out which formula you need to use. Law of cosines or law of sines. I don't know which one, but you'll figure it out. But yeah, I would like to see a diagram. I want to see stuff labeled. I want to see what you plugged in. And then I want to see your, final answer rounded to the nearest 1/10 of a degree. So, if you guys don't have appropriate work, you won't get credit. You won't get any credit for this problem. And I said this morning, if you guys, and I say guys, generally speaking, guys and girls, if you all Google any problem on this test or the TGA 1, 2, or 3, if you Google these questions to look up examples that look like it, that is considered cheating. Anything that I give you, you can use. I'm giving you a lot of hints and a lot of tips, and this review is I think is a huge help. But Googling questions, copying and pasting questions, that is cheating. And I can't catch everyone, but shame on you if you're somebody who Googles questions. That's bad. Don't do that. But anyway, thank you for joining me. And oh yeah, we need the password too, right? The password for your test. Password is upload part 2 as PDF. Case sensitive, all one word. I probably should have had this password like long ago, because I want you to upload your part 2, your TGA, in PDF form. And I say it like every test, and I write it on your test or like on the review, but a lot of you don't do it, and it makes me sad. So please upload it as a PDF. It makes it when I view it to grade it, the formatting is good. If you upload as just a Word document, if you just type stuff directly, and actually some people have touchscreens and they write, and I think that's awesome. But if you upload those documents directly, there is a chance the formatting could get lost in the conversion of when I pull them up to grade. So this is why I want you to upload as PDF, because, well, the formatting stays when I view it and I can grade it correctly. So there you go. All right. 5:30, hour and a half review, which is what I expected. Well, thank you guys for showing up, the ones that did. And good luck. Part 1 of the test is tomorrow. The part 2 is on Wednesday. We are starting Unit 5, our last unit, on Thursday. How exciting. And Unit 5 is long. It's a long unit. The longest unit. It's too long, in my opinion. I think Unit 5 could be split in half to make 2 more units, but whatever. It's a long unit. Oh boy. It's so long I haven't even finished making my lessons for it yet. That's not good. All right. Anyways, see you all Thursday, and good luck on your test.